Okay, hello everyone. In section 6.4, this would be the last section of chapter 6 for us. We're going to summarize everything that we learned about the conic sections. So it's a summary of conic sections. We're going to end this with the identification theorem, which is what this is really, identification theorem of conic sections. So here we're looking at the general form of all conic sections. Parabola, ellipse, circle, hyperbola, every one of them that we've talked in the previous sections and lectures, they all fit this general statement that you're looking at, the general polynomial statement. Now, depending on the values of a and c, that's what pretty much determines whether we are working with a parabola, circle, ellipse, or hyperbola. Now remember, a and c are the coefficient on x squared and y squared. In other words, when we identify the conic section, it doesn't matter what these are. Okay, and even the number, if the number is non-zero, that's okay. Let's say this is 15. I can subtract 15 from both sides. Now it's 0, and that f, which is the constant here, right in here, f will include 15, right? So if whatever f is 100 minus 15 is now 85. So it's okay for this not to be 0, but in general form, whatever constant f is, that will absorb the non-zero constant on the right side. What are important are a and c here. Okay, now one thing that's missing in this equation, by the way, if you look at the alphabetical appearance of the letters, we have A, B, C, D, E, F, right? Well, B, and the book skips B and it goes from A to C, right? And B, X, Y, that's the cross product term which is missing in this expression. The more general form of conic section actually has ax squared plus bxy would be in there. That would be the term right next to the ax squared, between ax squared and cy squared. So if it's missing, that means b is 0, which is fine. Then we get any one of these conic sections that we have worked with. What if that b is not missing, and we are not going to take that into this course? What if b is not missing? Well, if b is not missing, that means b is different from 0. Then in that case, we get a rotated version of the conic section. Okay, it causes the conic section to rotate. So for example, the parabolas may look like this. The ellipses may look like this, right? And the hyperbolas likewise could look like this, for instance. Remember this one we've seen before, the graph of 1 over x, which is an oblique hyperbola. So that's the effect of b on the conic section. It causes a rotation. All right, just want to point that out. But all of the ones we've worked with, b is 0. And if b is 0, then the axis of symmetry, the transverse axis, and the major axis in parabola, hyperbola, and ellipse respectively, those are either horizontal or vertical. Now, how do we identify these quickly? Very easy. All we have to do is look at a and c. If one of these variables, by the way, if x squared or y squared is missing, we know that immediately that's going to be a parabola. Okay, and look at this one. See, you have only y, only x. You don't have those in squared forms, whereas the others have x squared, y squared in them. So if the square is only on x or y, we know that's a parabola. But going through the motions, to have a parabola, either a or c, not both, because if both are 0, we get a line. Okay, so either a or c, not both, are 0. That handles the parabola. What about a circle? For a circle, a and c must be exactly equal. They must be the same. And they cannot be 0 again. Because if they're both 0, then we get a line. All right, and that gives me a circle. What about the ellipse? For the ellipse, the product of AC has to be positive. So that means A could be negative, C could be negative. That product is positive, or they both could be positive times positive. That product has to be positive. And they must be different, because if they're equal, then you get a circle. If A and C are equal, they become a circle. And for a circle, by the way, A and C could be negative. So I could have negative 2x squared, negative 2y squared, plus blah, blah, blah. That would be a circle. Because I can turn around and multiply the whole equation by negative. See, that turns it into a positive. As long as A and C are equal. But for the ellipse, they have to be different, and the product has to be positive. For hyperbola, the product is going to be negative, right? So for example, I have 5x squared, negative 2y squared. The product is negative, and see the difference between the squares, the minus. That's the sign that this is a hyperbola. And you see these examples right across from them. Now, we got to make sure the equation is in standard form, and by the way. So for example, something I make up real quick. Let's say I have x squared minus y squared plus 3x negative 4y equals 3y squared plus 7. Let's say if I want to identify which of the four conic section is this one, I cannot immediately say, oh, x squared minus a minus y squared. A is 1, C is negative 1, the product 1 times negative 1 is less than 0. This is a hyperbola. That's wrong. Why is it wrong? Because I have 3y squared on this side. Let's make it, in fact, negative 3y squared. There. Now, when I move this to the other side, this becomes x squared, negative y squared plus 3y squared plus 3x negative 4y minus 7 equals 0. So I get my 0 in that important position. Now, combine like terms, I get x squared plus 2y squared, right, plus 3x negative 4y minus 7, 0. And now I have, there you go. From this, I can identify that A is 1 and C is 2. The product 2 times 1 is 2, which is greater than 0. A and C are not the same, they're different, positive. That's exactly what an ellipse looks like. So this is an equation of an ellipse. You see that? Therefore, make sure we have it in standard form, all terms combined, and then we make the determination. All right, so let's do a few of these. We just want to identify these next examples. So suppose I have x squared over 49 plus y squared over 100 is equal to 1. Okay, now for this one, I can write x squared over 49 as 1/49 x squared plus 1/100 y squared, right? Minus 1 equals 0. So there's A, there's C. A and C are not equal. AC, the product is positive. Therefore, this is going to be an ellipse. Right in here. They're not equal, the product positive. If the product's negative, then it has to be a hyperbola. Okay, let's take a look at another one. Another example. Let's say this one, I have x squared over 4 minus y squared over 16 equal 1. You probably recognize these because we graphed them. This is a hyperbola, but let's go through the motions. I can write this as 1/4 of x squared negative 1/16 y squared equal 1. You can subtract 1, make it equal to 0, so it's in standard form. Again, here's A, here's C. The product of AC this time is going to be negative, right? It's 1/4 times negative 1/16, whatever that is negative. So that means this will be a hyperbola. See how quickly we can determine that. And next, let's take a look at this one. In this next example, suppose I have 4x squared negative 24x plus 5y squared plus 10y plus 41 equals 0. Okay, so what will this be? Well, for this one, let's work it. Now, sometimes this can be tricky. Okay, because we could be working with a degenerate case. Something that this one doesn't address here is the degenerate cases. Remember, the degenerate cases for ellipse and circle, they degenerate. Here's my double nap cone. For ellipse, the ellipse degenerates to a single point. The circle degenerates to a single point also, because the circle is just another ellipse. The parabola degenerates to a line, and a hyperbola degenerates to two crossing lines. So the one thing that theorem doesn't tell us is about the degenerate cases. So this one, if I just want to identify right now, I'm looking at x squared, y squared. This is a, that's c. Remember, this is not, negative 24 is not c. It has to be the coefficient on x squared, y squared. So if I look at right now, a is not equal to c, and ac, the product is positive. So I'm going to say that this is an ellipse, right? But let's work this one out. It will be interesting in this one, what is going to happen. So I'm going to go 4x squared plus 5y squared. I'm grouping my y terms. Now let's group the x squared together like I always do. Let's group our x's together, and plus let's group our y's together. 5y squared plus 10y, right? The constant, I'm going to move the constant to the other side. We don't want it on that side. All right, now let's factor the 4. I'm about to complete the square, so I need the coefficient on x squared to be 1 minus 6x, and from the y I'm going to factor the y. That's going to make it y squared plus 2y, and of course negative 41 on the other side. Now let's complete the square. Half of negative 6 is 3, negative 3 squared is 9, half of 2 1 squared is 1. And don't do 9 1 on the other side, because there are numbers outside parentheses. We gotta be mindful of those. 4 times 9, I'm gonna add 36 here. 5 times 1, I'm gonna add 5 here, and this is going to give me 4x minus 3 squared plus 5y plus 1 squared equals, check this out, 0. Now, at this point, the only thing that works here that makes this 0 is if this is 0 and that is 0, right? 0 plus 0 makes 0. So x has to be 3, y has to be negative 1, right? So so that's 0 and that's 0. 0 plus 0 becomes 0 by inspection. Therefore, this is a degenerate ellipse. This one is going to be a single point, a degenerate ellipse, 3 negative 1. So if we were to graph this, by the way, everyone, 1 2 3 negative 1, the graph is just that. You see, it's not an ellipse, it's a degenerate ellipse, and there you get a single point, 3 negative 1. That's the graph of it. So the correct answer to this one, if we were to answer which of the conic section, we're just going to call this a point, and that's all that is. It is a point. Okay, let's take a look at another one. For this, just a couple of more and we'll be done. Let's say we want to graph these now. X squared equal 25 plus y squared. All right, so how do we know which conic section? First, we need to identify it. So I'm going to bring x squared, y squared to the other side, minus 25 equals 0. or just set it equal to 25. Let it be 25. Because once I identify, I can graph it. So this is A is 1 and C is -1. The product AC would be -1, which is less than 0. So this will be a hyperbola. That's just the identification part. Now, how do we graph hyperbolas? If you remember, we have to have 1 on the right side. So next I'm going to divide both sides by 25. That'll give me -y squared over 25 equal 1. This is going to be a hyperbola that's centered at 0, 0. A squared, B squared are equal, right? 25 each. So I'm going to go right 5, left 5, up 5, down 5. And draw my fundamental rectangle here, which is going to be a fundamental square actually, right? Because the denominators are the same. So the rectangle becomes a square. Draw the lines, the asymptotes that is. And this one, because the hyperbola starts with x squared and then it's minus. So it's going to be, the transverse axis is going to be horizontal. And I got to be careful here. There you go. Because it's going to go, the center is at 0, 0, right? There, center is at 0, 0. So these diagonals have to go through 0, 0. Okay, this is good. And the transverse axis will be horizontal, so I go to the edge of the box and draw one branch, right? Go to the edge of the box, the other box, the left side of that box, and draw the other branch. This is at 5, that's at -5. And there you have the graph of this one. Okay, now, well, let's see. Let's try our last example. Let's say in this example, the equation, let's go to general equation, 4x squared. Okay, 4x squared, -8x plus 9y squared, -36y equals -4. Now for this one, again, make sure we look at just the square terms. So A is 4, C is 9. AC is 4 times 9, 36. Positive. A and C are different, so this one is an ellipse. Right? We identified it. Let's graph it. We're going to group the x terms together, plus group our y terms together, equal -4. And then factor the 4 from the first binomial. Factor the 9 from the y's. And let's see. Okay, to complete the square, we're going to go half of -2, which is -1 squared makes 1. Half of -4, 2. 2 squared is 4. And what do we add to the other side is, once you distribute, we're going to add 4. And we're going to add 36. 9 times 4, that is, on the other side. Okay, and this is good. Now I can write the binomial form of this is x minus 1 squared plus 9 y minus 2 squared equals 36. Remember, for ellipse and hyperbola, we have to have 1 on the right side. So let's divide everything by 36. This one gives you 9. 9 times 4, 36. We're dividing by 36, so this becomes 4. 36 by 36 is 1. And there is the equation of the ellipse. And the center of this ellipse is going to be at 1, 2. Right? And then we can graph the ellipse. Center is at 1, 2. Here's 1, here's 2. Okay, 1, 2. So I'm going to go square root of 9. That's to the right, 3 to the right, left. Let's make it more to scale, otherwise my ellipse is going to look terrible. There you go. So I go right 3, left 3. Right 3 from 1, add 3, and then take away 3 from 1, we get -2. And then from here, I'm going to go up 2, down 2. Well, this was a 2, down 2 puts me here, up 2 puts me there, it goes to 4. And then we can draw that ellipse. Here we go. So we got it. That's going to be the graph of the ellipse. Okay. And you can go through all the details that we went earlier, right? We can do the vertices. Let's do the vertices because they're easy to do. The vertices from x started at center 1, then we went plus minus 3, and the height is 2. Those are the vertices. What else? That should be good enough. Don't worry about the foci eccentricity and all that stuff. So I go 4, 2, and the other one is -2, 2. That's VV prime. All right, and with that we are done with this lecture, rather short lecture compared to the other ones. And hopefully, again, you find this easy to do. The key idea of this section was to identify the conic section, and we can graph them like we did it in previous sections. So as always, thank you for watching, and we are at the end of this video.